Except we've got a really fantastic session today, and I can probably begin the process of introducing Benjamin Monate, who is the CTO and founder of TrustInSoft. We're really excited to have him here. Every once in a while, I have people who drive from as far away as the East Bay, and I think that's crazy. He flew in from Paris to speak here this evening on formal methods and a mathematical proof of zero bugs in code, which is an interesting conversation. It usually starts with people asking if that's magic. And in fact, it is not. But we'll get into that in a bit. So with that, I'd like to introduce Benjamin Monate up here, Silicon Valley, live and in person, to speak to all of you, and then, of course, to answer questions, hopefully some of them challenging.
Thank you, Mike. So thanks for the invitation. I'm very proud to be in front of you, and I will share with you my thoughts about formal verification and the questions that many people have in mind about the security of firmware. So let me first introduce what is a firmware very quickly. I know most of you are familiar with that, so I just select the part of what is a firmware that will be of interest for the rest of the talk. So firmware is a kind of software that's embedded deeply into hardware. That's usually the lowest layer in a programmed system, so just above the hardware, above the chips. And its main goal is to control the device functionalities, and the devices can be of many different kinds. You have firmware in your phone, in your game console, in your server, in the cloud, in your hard drives, mostly everywhere. In fact, you have firmware everywhere, and they are hidden. Usually you don't see them as the end user because you have interfaces on top of that. You have tons of layers on top of firmware, but it all starts there with these small pieces of code. Well, I say small, but they used to be very small, but nowadays they are very complex because the hardware itself is becoming very complicated. System on chips are more and more complex and implement very complex accelerations at the hardware level, and it means that the firmware needs to cope with that and to handle it better and better. So you can even find some implementation of complex protocols within firmware, which is what was not so common 30 years ago when the first firmware were written. Quick word about formal methods, and I'll go deeper on these topics during my talk. So what do we mean by formal methods usually? Formal methods are techniques. I say techniques with an S because there are several techniques that are under the name, that go under the name of formal methods. And what they share is that they are rooted in mathematics. So there is some math behind that. I will give you some more intuition about what it means to have mathematics behind a method. What are they used for? Well, they are used for several things, but here for firmware, they are used for verification of software and hardware combinations. So sometimes only on hardware, sometimes only on software, and sometimes on the combination of both. And this talk will focus on the software level only. And what are they used for? What kind of verification do we do on software, for example, with formal methods? In fact, we prove properties. And let me spend a few seconds on what it means to prove something. Proving is a mathematical notion. It's a way of establishing a fact that is universally true. Typically, if you studied math some time ago, maybe a long time ago for some of you, but not so long ago for others, you remember that you had theorems, lemmas in mathematics. And what are they? They are statements that are true once they are proven. So you prove something and it's true whatever happens, whatever the conditions. Of course, you have application conditions, you have hypotheses, assumptions, but once they are verified, you know the outcome of the theorem always holds. And proving a property about software is establishing something universally. And what does it mean universally for a software, for a firmware? It means whatever happens in the real world, whatever happens on the hardware, whatever happens on the sensors, whatever happens in the environments. typically whatever a hacker may try to do, because it's part of the rest of the world, the hack. Why is it important to take care of the security of firmware? First, because firmware is one of the pieces of software that really matters to protect against the attacks against the system. This is the lowest layer, and a lot of people are trying to attack that, and the firmware is trying to protect it. Also, that's very important because you need to ensure that the device is functioning properly. And if you hack the system, if there is some security flaw here, then it means that someone will take control of the system, of the firmware, and make it do something else. And you don't want someone to take control of your hard drive and do something else with it, maybe mining Bitcoin or something like that. But that would be maybe not the worst thing to happen, but it would still be not a good thing. And also, why is it important? Because as I said in the beginning of the talk, I mean, you have firmware everywhere, and people are using those systems, all of the system, and the user, they need to trust the system. And if there is some hack some attack that's possible at the firmware level, then the end user can no longer trust any system around him, and that has, of course, enormous consequences. What's really important about the security of firmware is that security of a computer system is established in layers, and the lowest layer is usually called some kind of something like root of trust. That's a place where you have the initial trust in your system. Usually nowadays it's based in hardware. You have some kind of secret key embedded deeply in the hardware, and just on top of that you have the firmware. That is, and the firmware is supposed to preserve the root of trust and to establish that. So if you can hack that, you are breaking the trust of the system, the complete trust, and you can no longer trust it for anything. Let me give a few examples of firmware that have this notion of root of trust. For example, you have the trusted execution environment, TEEs, well, quite useful nowadays. And these systems, you can find them in your phones, for example, and you can also find them in very complicated cloud systems, because typically a TEE is a kind of software that allows different execution to happen in the system without interference. And you have to have those trusted execution environment in place and to be able to trust them. You also have firmware at the root of trust for security chips. We have more and more dedicated chips that are performing some security features. Maybe they are just doing encryption, accelerated encryption. You even have that in standard processor nowadays, but you still have a lot of dedicated processor for security, for cryptography. But you also have very complicated chips for example, biometry, for finger detection or facial visual detection and things like that. And they are more and more complicated. And again, there is firmware there, and the trust of the system relies on the security of the firmware. And bootloaders, of course, the things that start up all system around you. You have, I say bootloaders with an S because you usually have several bootloaders in a single systems, and all of them have to be secured. Otherwise, someone can take control of the system at the boot level and make it do anything he wants to. So really, security of firmware is important, and it does matter. And why is it challenging? Because security matters everywhere, of course, but firmware has special problems. First, it's very hard to patch a firmware. Sometimes it's even impossible. Some firmware are written in ROM chips, some chips that are read-only, that are written in a factory, and you can no longer update them. And once you produce a device and deliver it to the public with a few millions of items, if the ROM has a security bug in it, I mean, your device for all its life will have this bug, and you will not be able to fix it. So that's a problem. And even if you can patch it, if you can update the firmware, that's usually a very risky operation, because as this is low-level code, if something bad happens, I don't know, maybe your power gets down at the moment you update, you will basically kill your device. You will break it, as we say, if you are used to hacking your phone. You break your phone, I mean, you can no longer switch it on at all. So that's a problem to update a firmware. And if you have a sophisticated over-the-air update system for firmware, that becomes another security problems in itself, because maybe someone can hack the update system for it. So really, that's quite challenging on several aspects. Another challenge is the complexity of the new firmware. In fact, they are implementing more and more complex functionalities, and it makes them very hard to secure because they do a lot of things. And last, often this is completely overlooked. People don't know that it exists, and people usually forget about the firmware. This is not as true today as it used to be a few years ago, because people are more and more aware of the fact that firmware is a vector of attack, so they take care. But usually they don't talk about firmware, but they say something about the supply chain attack or something like that. But usually it's related to the fact that there is something that has been supplied to them that has a bug in it, and usually this is a firmware. So not only, but firmware are mostly guilty of all that. So, okay, what can we do with formal methods for security? So as I said, it's a way of proving properties. So what can we prove, and how can we help security there? First, even before proving, we can use formal verification and formal methods to identify potential vulnerabilities. That's the first thing. A lot of other techniques can help you do that. You can have people trying to pen test the system, or fuzzing the system, or expert trying to hack it and understand the architecture. But formal verification is one other way to find bugs. So that's already useful at this level. And then you can do something more. You can also prove something about the security. If you can identify vulnerabilities, you can define what is vulnerability, then you can prove the absence of vulnerability. And that would be a first very strong property that you really would like to have on your firmware, the proof of absence of vulnerabilities. I will tell you a bit more about that a bit later. Of course, if you have this proof, you can also make the proof of correct operation. That's not exactly the same property, but that's similar in spirit. And all of this, why do we want to do that? To prevent unauthorized access, basically. That's the major goal of all these techniques, to control who is able to do what with which system. What can we do if you don't have formal method, which is nowadays a common case, of course, if you want to prevent security problems? At the software level, you can do code reviews. Have very super experts read the code, read again the code, and read again the code as long as they can, and they will find problems and they will help fix the problem. So that's some activities that you can do. Then you can think a bit more about the process and say, okay, maybe we should impose some styling rules, some coding rules for the software to try to avoid some kind of vulnerabilities, some naive errors. So you do that to help the developers not do mistakes. And that's a good thing. I mean, that's a way to try to prevent. I mean, if you are making a cake, you definitely want to check that your ingredients are correct and are not too old. So that's the same here. But it does not mean that in the end the cake is good. It just means that at least you start with a sane base. You can do testing. That's the large majority of the activities we conduct on software. Test it. So we give inputs to that and watch the output and check whether it's okay, whether it's crashing or it's fine. Problems with those three approaches and three kind of activities is that they are basically endless. You can always do more. You can always do one more test. You can always add another coding rule. You can always spend one more day reviewing the code and re-reviewing it. So what do people do for that? Well, they just spend money on that. And when they have to deliver the product, they deliver it and say, okay, we did our best efforts and that's it. And that's the state of the art of security for the software nowadays. And it's working okay in some cases, but for very sensitive software, that's not enough. I will now focus on one special technique of formal verification. I don't have time to explain all of them, and I will try to explain one specific one so that you understand why mathematics help to solve those problems. So the method I want to discuss is abstract interpretation. So abstract interpretation, I will explain the word a bit later, but what is it? It's a way to do static analysis of source code. What does it mean? It means that's a technique of analysis where you don't have to run the code. You will just have a tool that looks at the code without compiling it and without running it. That's what static means. What will you be able to do with this technique? You will be able to prove the absence of coding errors that matter. So what does it mean, coding errors that matter? I may give a bit some more details later, but it means the errors that can lead to a vulnerability that can help someone take control of your system completely. If you're into this kind of thing, think of buffer overflows, for example. Number one kind of bugs that lead to complete control of systems. And why would you learn this kind of techniques? Because you want to replace some kind of robustness testing or security testing that you perform endlessly nowadays, and you want to replace this activity with something else. So you will be able to do that with abstract interpretation, and I will tell you more. But first, let's go back to the basic and explain again. This should be obvious to you, but I prefer to redefine the word step by step so we all agree on what it means. So what is a program? What is a software? A program at the most highest level you can think of is an operation on some form of data. What are data? Integers, numbers, strings, advanced data structure. If you have taken some computer science classes, you remember the things about trees and lists and heaps. Well, you know those words that you learned in school. And the program, this is just the description of the operation you want to do. And I will take a very simple example, a program that I name P, that takes as input a number, an integer. It's called data, and just adds 1 to this data. That's the P program that's on the slide here. Of course, this looks very simple, very simple. This is C code here, and all of you can read that. What you have in a firmware usually is not as simple as that, but the function just below is the equivalent of this function at the firmware level. So instead of reading some data that you take out of blue, your data, in fact, is read in memory at the address 42, where there is probably some kind of device that is mapped. So you have some hardware that is giving you data real time, usually. It can be a temperature sensor or something like that. And this function is just reading this data at the lowest level of the program and adding 1 to it. So this function really looks like what you could see in a firmware. So you're reading from memory, in some places in memory, and do some operation. So this is a program. Now, what does it mean to run this program? Well, running, it means having a concrete execution for specific values for the data. For example, if you use the value 255 and you run P, the outcome is 256. And this is exactly an execution. So one value, another value. And you do that value by value. Right away, you can see a problem there, the number of possible values. Here, I assume a 32-bit architecture for the people that want to go into the details. And it means that I have over 4 billion different values for data. And that's for the program named P that was less than 1 line. So that's the most simple program you can imagine. And even for this program, you have over 4 billion of value. In fact, that's 2 to the 32, if you want to be exact. And of course, what you would like to do, if you try to prove something about your program, is to predict the possible outcomes for your program, whatever the values. So how would you do with traditional methods? Let's focus on testing. Well, you would have to write 4 billion of tests. Of course, that's not possible. That's untractable. You won't do that. And even if you manage to do that for 4 billion, if I add another variable, this is the end. This is more than the number of particles in the universe, so you won't be able to do that. So that's why we invented abstract interpretation. Well, I did not invent it, of course, but some very famous researchers invented that before me. So we invented abstractions because we wanted to deal with huge number of values at once and be able to reason about them. What is an abstract value? That's a simplified representations of a large set of real values. Very simple abstraction, for example, if you can abstract a number with considering only its sign. So only instead of having 4 billion different values, if you abstract them by their sign, then you have only 2 values. It's either positive or negative. So you are reducing a lot the number of possible values. You only have 2 values at the abstract for this abstraction. Here, for P, in fact, we have a natural abstraction. I said in the beginning that the data was in an integer, an int, in C. In fact, this is already an abstraction about what is the value of data, and this is a very condensed abstraction. And the exact abstraction is written on the slide. It's somehow an inequality between -2 billion and 2 billion. And this representation, well, it's only half a line, and you have all the values there. And the abstraction is this representation, this way of describing the set of values. That's very compact. I mean, if I write it with letters, you see I have 2 numbers and 1 word and 2 signs, so that's very compact. If I had to list all the value, to enumerate the values, of course, I wouldn't be able to do that on the slide. So this is the idea behind abstraction. So instead of manipulating values, I manipulate these abstractions. Now let's go back to the notion of predicting the outcome of a program, what the program does. We want to do those predictions without enumerating the values because we cannot enumerate them. So we can do that for P. As input, my abstraction was this inequality. And with this, that's quite easy, in fact, to compute exactly the output in this abstraction domain. And what is it? It's, again, between -2 billion and 2 billion, but if you look at the last digit of the numbers, they have been incremented by 1. So in fact, you have shifted the interval by 1. And the operation that does this program is this. It transforms this initial interval in an interval shifted by 1 to the right. So this is only 2 operations, in fact. You see, +1 on the left bound and +1 on the right bound. And this is how we manage to cope with the billions of value instantly, in fact, because now we just have to do two additions and we have the results. And now we live in this abstraction and we no longer manipulate concrete values, we just manipulate the sets of values and we know how to compute exactly the operation on those values. So this is not magic, this is purely mathematics. And we need to design these abstractions so they are simple enough, but they are precise enough to make good predictions. Because if I go back to the first abstraction I took as example, the sign, that's not precise enough. You won't be able to guess a lot of things about what your program does if your abstraction is just keep the sign of the integers. You need more. So you design abstractions that make sense for the developers, because when you are a programmer and you develop code, in fact, you build those abstractions in your head implicitly. You've been trained to that. So you reason about what you do. And we need to mimic that in tools that can reason mathematically and check for your errors. So I gave some examples of abstractions, a small set of values, set of 3 values. In intervals, exactly the one I used for the slide before. And you can add some more complicated abstraction like intervals with congruence constraints, typically all the even integer between 0 and 256, or more complicated things, and all the usual notions that the developer has in mind. Interval of floating points, with maybe a special case for special floating point numbers, the various nan, infinities, and zeros. You have the notion of pointers in C program, for example, and you want also to abstract the notion of set of pointers. But that's only notions that normal engineers can understand because that's the way they think about their program naturally when they are trained as programmers. And now, thanks to the abstractions that are precise enough and readable by the engineers can understand what the mathematical tool gives out as output. And understanding the prediction made by the abstract interpretation is another way of telling that the people can fix the bugs that are discovered. And that's the goal. Remember, the initial goal, it was to fix the bug, to find all the bugs, to prove there are no bugs. And if you find a bug, you want to fix it and prove then that you no more have any bugs. And this is exactly what the abstract interpretation is helping you to do. You have to be very careful when you design the abstraction and the operation of these abstractions because you want to be mathematically sound. That means you want to see all the possible behavior of the program. You don't want to forget about some values. And if you are a user of classic static analyzer, you know that there is this notion of false negatives. A false negative is a bug that your analyzer does not find. And if you are dealing with mathematical methods, you have to design abstraction in such a way that there are no false negative. And when we say that we can prove the absence of bug, prove zero bug, it means there are no false negatives. It means whatever is not seen by the tool does not exist. So if the tool says, I can't find a bug, it means there is no bug. And this is the notion of proof that comes from the mathematics that is used there. Also, of course, this abstraction must be designed so that they can capture the bugs that people do and the families of bugs that really matter. And for the C and C++ standards, for example, there is this notion of undefined behavior that is basically the entry point for all hackers in software, especially in low-level software. But that's important, but that's not the only thing you need to have. You also need to be able to go back to the root cause of the problem, because if at some point of the program you identify a bug, usually the fix will not be applied at this location. The problem comes from earlier in the execution path, and you have to find a way to trace back to the original values, to the original abstract values that contain a value that was dangerous for your code and that should not be filtered somehow. And so you have to design those abstraction computation and keep track of all what has happened in your program. So those mathematical predictions are sound, and they allow you to automatically find errors, inefficiency, or security risk in the programs. So let's wrap up quickly. So thanks to abstract interpretation, you can understand your code. You can exhaustively explore the behavior of your program. Because you are no longer running it on single values, isolated values, but on abstractions and interpreting on very large abstraction, mathematical abstraction. And you can do that in a much more manageable way than enumerating all the possible values. For firmware, it means that you can prove the absence of vulnerability, whatever the state of the memory or of the sensors of your hardware. And that's a very important property, because basically if you want to hack your hardware, you will just try to put in the memory the values that will cause it to crash. So if you can prove that whatever the memory contains, it will never crash, then you have a very strong security property. Just small info on P, there is a serious security bug in P. It's a sign overflow. It's called CWE190. That's a very famous one, and I think it was the cause of the last very large security issue in WhatsApp, for example. So it looks very innocent, but it was exactly this kind of bug. Yeah, OpenSSL too. I mean, there are tons of stories about sign overflows, and this is one example. So to make this usable, of course, you have to have tools that are capable of simplifying the presentation of the results, because I've discussed mathematics, abstractions, and if you dump to the user all you know about your program in your abstract mathematical world, this is intractable and you cannot read it. So you have to be able to understand as a user what your tool did and why. And here, typically, people are interested in checking the coverage of their code, whether they tried their code everywhere or not. And this is very important to know that you can measure this kind of thing with abstract interpretation, because basically you are propagating values along the execution path of the program, exactly like a test would do, but in a more general way, so you can transpose the notion of coverage to abstract interpretation. So that's very important, because if some piece of code is not covered, it can mean several things. Maybe it's not covered for a bad reason, because of a bug that prevents you from reaching the security measures that you implemented in this piece of code. Or maybe you misunderstood the inputs of your system. And if you, as a tester or verifier, misunderstood what are the inputs, maybe the hacker will understand the inputs and use that knowledge to hack your system. Another thing that's very important is something very common in software development nowadays. You want to shift left everything. So check your code as soon as possible. Don't wait for production to check things. And you should do the same with formal verification. You do that as soon as possible. And formal verification, in particular abstract interpretation, is very adapted to these kind of things, because typically, it applies on partial code. You can interpret only a few functions if your system is not completely developed. You don't need the underlying hardware. So even if the hardware is not available, you can already try to check your software and know in advance whether you have security bugs or not. So that's very good techniques if you want to implement shift-left approach for verification. And of course, you have to integrate that in your processes and do continuous verification, because a single audit is not enough. You have to check your code again and again, because each line of code can introduce a serious security bug that has huge consequences for the whole system. It does exist on real systems. This is a screenshot for the tool we develop at TrustInSoft. And this is for the P program, and you can see that indeed, for real, some developers can see in a somehow familiar environment, so it looks like a development environment, can see exactly what has happened, and you can say, okay, this operation can overflow with this value, and this is what's written here, there, and we discussed a lot about prediction of possible output values, and this is written on the bottom right here. You have a prediction. You can see there is no 8 here on the right-hand side, because in fact in C, the 8 is not representable here. So the system knows that and say, okay, the only possible value are these values. And there is a potential error if in fact you were 7 here and you try to increment 1. That's a sign overflow of OpenSSL or of WhatsApp. So best practices for using formal methods. First, you have to make your assumptions explicit to know what are the inputs of your program and what can you expect from your environment. If you are reading something from a sensor and the sensor never returns something outside 0 and 255, for example, you have to know that, because your code probably doesn't try to protect itself from other values. Or maybe you don't want to rely on that. Even if the sensor is not supposed to give values outside this range, maybe you want your code to be resistant to someone that would manage to inject arbitrary values that are usually not legal for this sensor. And people are using the technique called fault injection to check whether they can hack the system. Well, with abstraction, you can easily inject faults, because you just have to tell the system, okay, this input can contain anything, even something that's not within the specification. So that's very important. You have to perform regular audits of your verification to know whether your assumptions still stand, whether your coverage is still okay. You cannot just trust any kind of tool and say, okay, this is fine, my security problem is solved forever. Each line of code can introduce new problems, so you have to regularly review everything output by the tools to check that you are still on the safe side for security. And of course, you have to integrate that in your process, be it within the tool chain or a manual process. You have to check that on a regular basis. You do this kind of verification. Well, thank you. This was my introduction to formal verification and firmware security. Hopefully you got something out of that. I'm here to answer any question you may have on these techniques. Thank you. Thank you.
All right. So I like to start these off with my first question, which is generally the same. You've done a lot of stuff. You started TrustInSoft. You got into this a long, long time ago in research in France. But at what point did you think, you know what? I think I can make a job out of this. This could turn into a company. And when did you have that epiphany? What was it? And how huge was it? Were you thinking maybe I can make a living or maybe I'll change the world?
Both, I think. But mostly changing the world was my intention and still my intention. Yeah, I think that we have been building software with empirical method for too long. And mathematics are a way of solving this problem. So my goal is to change the world of software development. Not the whole world, just the software development world. That would be a first step, and we'll see for the next step offline. But yeah, changing the world of software development because, in fact, code is not some kind of raw material. I mean, that's completely formal. I mean, this is perfectly defined what software does. In fact, it does exactly what's written, and the problem is a mismatch between the intention of the people that write the code and the code itself. And mathematics is especially adapted to prove that both match.
Nice, thank you. And also, we do have the ability to take questions from people who have joined us on the teams, and a huge shout out to people who have joined us from as far away as Tokyo and Korea on this call. I saw you sign up. I'm excited you're here. I know you have questions. So jump in, ask questions. We've got the security team from KPMG Tokyo, and also Slexon in Korea has joined us. So if you guys have questions, I want to hear from you. And also the audience, if you do have questions, we've got microphones. So let's go ahead and ask questions either there or, I don't know.
I'll start us off, Mike.
In any case, John, go ahead.
So there's a mic on the other side. So if anyone else would like to queue up, grab the mic, or might be getting our online questions. For those of you who don't know me, John Donovan, past president here. First of all, Benjamin, thank you so much for a good, deep talk. For some folks who have maybe the engineering background or the mathematical background, you're probably blowing a lot of people's minds who don't have that. So my first question is kind of a simple one. I know you're focused on firmware, and this is such an important part of it. Can you apply some of these same techniques to further up the stack, as it were, in the software stack?
Yeah, of course. I mean, I focus on firmware for this talk, but firmware is probably a quarter of our customers, and the rest is other software on top of that, and up to server level software. So,
thank you. And if someone else wants a question, raise your hand. I'll pass you the mic. You're too far away. You have to get the other mic.
I can pass you the mic. Or you got it?
Yeah, inside the microphone here.
Well, yeah. for the people who are joining us on the teams, it's just easier.
Who?
My name is Atul.
Okay, go.
Go ahead.
The question is that I'm looking for the real use cases in real world, like John was talking about the further up in the stack. Can you give some example of your customers? Probably if it's secret, it's fine, but you can say customer A has this use case, customer B this use case, maybe if it's appropriate.
Okay, so a few examples. Of course, our customers have strict NDAs, so I can't drop names publicly and things like that, but I will give you global examples. So one of our customers is developing TEEs for phones. So from the ROM level to the highest operating system level and drivers and all software in between. and they need to prove that they are security resistant, that whatever the hackers does, you cannot take control of that. Otherwise, you could take control of the life of people that are using the phone. So that's one kind of example in the consumer electronic domain. Another one is, again, in consumer electronic, is game console. When you are running a boot game console, you have to check the integrity of the boot chain up to the operating system, and we have customers in this domain. In a completely different domain, in embedded critical systems, you have people in the aeronautics that develop software that goes into plane, and if you fly frequently, you will be happy to know that some of this software have been proven to be secured or safe. Autonomous driving, also in the car industry and connected cars, there are a lot of software that are very sensitive, and there are a lot of things at stake there on this.
Thank you.
You're welcome.
All right, thank you. We had a question there.
Yeah.
Thank you, first of all. But is this, and I think I know the answer, is this limited to just the C language, because you gave the C example, or can it apply to any other platform?
So in theory, the language is not a problem. You can adapt that to any kind of language. In practice, there are not so many solutions that implement this in an industrially usable way. In my company, we implement a solution for C, and for Java.
Okay, so it can, and then is something a quality engineer can run, or is this something that the developer runs? What does the process look like? Who does it apply to?
So the people that have to use the tool in the beginning are testers, developers, testers, to set up the analysis, to define the assumptions, to say exactly what functions they want to do. And then the people that run the tool and collect the results can be QA engineers, of course, because it's running in the CI, and then QA engineers know how to collect those things and give feedback to the developers and identify who is responsible for which piece of software and things like that. So both. Was that?
Yeah, as a continuation, thank you for joining us, by the way. Very interesting talk. As a continuation from that, on product security side, although we have developers, I mean, it's hard to bridge communication gaps. You have possibly 5-10 years of technical debt. The developers that were there in the beginning that wrote that code are gone. There's not a lot of documentation. So in a practical use case, what's the barrier to entry to getting this in? It's not a silver bullet. Nothing in security is. So clearly there is a benefit to this, but there is, at least from my perspective, some barrier to entry. Can you perhaps, as a continuation from that question, how do you sit down with an organization? Because unless this is brand new code and you're introducing this in this practice at the beginning, how do you take into consideration decades of technical debt? That's it.
Thank you. Very interesting question. First, I think code does not remain new very long. After a few weeks, this is no longer new code, and people lose control of it. Because even if people are still there, they forget about it. So we are always dealing with some code that no one knows. At least no one knows at the level of details that is necessary to be able to be certain there are no security problems. And that's why there are a lot of security flaws everywhere, because everybody forgets about the details, the precise details. And in fact, the barrier to entry is not that you should know the code in advance, because you don't. That would be meaningless. But the barrier to entry is someone must be able to write something that looks like a test. So you need to be able to say, okay, I want to call this feature of the program in these conditions. So I want to try some, maybe for cryptographic library, I want to call the encrypt function with a buffer of size 20 with any content inside. And you have to be able to say that. If you know how to do that, then you can use the tools for abstract interpretation. That's all. Of course, you have 2 or 3 days of training to know how to use the tool, like any other tools. But the real barrier is to find someone that is able to say, okay, I want to test this functionality with this kind of input ranges. And someone that is capable also of interpreting the results and fixing the bugs. Because if you find bugs, but you can't fix them because you don't master the code, then you're at lost. But it does happen, even in serious companies, because you can't keep track of everything. So you have to identify the code where it matters and where you are ready to pay the price of fixing the bugs. And most of the barrier, most of the cost of usage of our tooling, for example, in TrustInSoft, is the price that people pay to fix their bugs. And for people that have very few bugs, this is very cheap to use the tooling. But this is not the common case.
That was a great answer.
Yeah, thank you. And in fact, if you think of the economical point of view, it means that your return on investment must be computed with the idea that you have a cost to your bugs. And you have to know this cost, and knowing exactly how much a bug costs you in your organization, that's something very complicated. And in our sales process, most of our work is to find out with our prospect and customers how much does a bug cost them. And when they manage to measure that, usually they buy our tool and they continue forever. But that's still a barrier to the entry, to be able to identify that, to build this ROI completely.
To follow on to, you mentioned a couple of languages that you currently have practically going on, C, C++, and Java. What would you say would be the difficulty in taking some platforms such as the JVM and trying to apply these same kinds of things to the code that's already generated? One of the things is the testers and all that sort of stuff at the front end, and the folks doing development. But I, as a consumer, getting this code, not necessarily getting the source code, getting this generated stuff for WebAssembly or any of these other kinds of interpretation pieces, what would be sort of the future of being able to say, I'm getting this thing, do I trust to run it or not? Or are there, are the same number of vulnerabilities in there that the developer said was there, that sort of thing? Is there's some future to that you can envision being able to do?
Okay. First, we could imagine to apply these techniques to very low-level languages like assembly or whatever bit-level languages you can imagine. But doing that is very dangerous and very complicated. Very dangerous because your tool chain, your compiler, may make some bug disappear for wrong reasons. And it means that you can prove that the generated binary, if you are at the binary level, seems to be working, but in fact you change one line of code somewhere else, and then your binary instantly is completely flawed. So that would be the first problem of analyzing this. Then, of course, if you're analyzing this kind of language, you have lost all the structure, all the intention of the developer. So it makes it even harder to reinvent and refine all the abstractions that were present initially. And if you have feedback to give, third item, if you have feedback to give to the developer, if you are talking to your developer in terms of registers and stacks, when he develops something in Java, he will have a very hard time to communicate with him to explain what's wrong, because he just knows that there is some crash. And well, this is what you do when you have a crash in the field. I mean, you just have a core, if you're familiar with these notions, that's a dump of the memory and the registers. And you tell the developer, okay, go, there is a bug, fix it. And you know what the answer of the developer to that is that I can't reproduce that. I mean, I cannot make sense out of this dump of the memory. And so you will have the same problem with formal verification there, that the predictions would be completely impossible to understand for the end user. And then there is this question of trust in your tool chain. That is, if you prove something on your source code, does it hold on your binary? And that's a very interesting question and very deep question. What we suggest to our customer is that when they have this kind of thing in mind, is that they should validate their compiler independently of their application. So that's the way they do in safety critical system, where there is this notion of qualification according to a standard, where you qualify your compiler for your usage pattern. And qualifying your compiler means it makes a binary that is exactly implementing the semantics of your source code. And then you prove things on your source code, and then mathematically you have a diagram that commutes, and that says, okay, your property holds on the binary. But again, that's mathematics there. There is a theory behind that, category theory, that explains that in detail. But the idea is quite intuitive. That is, if you prove an equivalence between two objects, and you have a property on one object, and it transposes on the other one. So that's a few comments around your question. I don't know if I answer completely, but that's what comes to mind.
That's good, and I appreciate you.
Thank you.
Great, thank you. So we're going to wrap the Q&A, and Benjamin, thank you again for coming. This was fantastic.
Thanks for the
And the
invitation.
conversation continues over drinks and food, so please do join us. Should be a lot of fun. And for those of you on the teams, thank you for joining us as well. And yeah, look forward. It's that way.
Thank you very much. Thank you.